Give me some water, because I'm thirsty. I'm a thirsty individual. Okay, so check this out. We know that for Ampere's law, if we go on the outside of a wire and draw an Amperian loop, we'll find that the B field is equal to mu naught I over 2 pi r. We can do this for Ampere's law, or this is the Biot Savart, right? But what happens when we go inside the wire itself? We know there's a B field in that wire, but what is it? So let's take a look at this. First, I'm going to create a cylindrical wire, okay? And for this cylindrical wire, we're going to say it has a current passing through it. School's over. A current's passing through it. We're going to call it some current I, okay? And that current is coming out of the page. So it's coming towards you right now. Now, if we were to create for ourselves an Amperian loop inside of the wire, we'd have an Amperian loop that looks like this, where this loop is centered on the wire. It is some radial distance away, r, for this loop. And the cool thing about this loop is whenever we go around the loop, our thumb points in the direction of the positive current, so we wrap our fingers in the direction of our Amperian loop. Thumb points in the direction of current, so this current's positive. And what's nice is that the B field that this wire is going to generate, the B field is going to be in the same direction of this loop, so that at any given point, when we take a small bit of the loop here, a small bit of ds, it is in the same line as the B field dB here. So what we're going to find here is if we set up an Ampere's law where we have the closed path integral of B dot ds, and remember that dot product represents a cosine of theta term, since our B field and the path vector we're walking on are in the same direction, this will be B ds cosine of 0, and the cosine of 0 is 1, so I can ignore the cosine of 0 here, okay? So all I really need to worry about is that this is going to become B times the closed path integral, and we've talked about how this closed path integral is just, well, what's the length as you walk around the circle? So this is just going to become B, and that circle length is just 2 pi r. It's just the perimeter of a circle. And we know from Ampere's law that this equals mu naught times the the current enclosed within our loop. Now here's the thing. This current here in blue, that's the current for the entire wire. And I don't have the entire wire here. The only amount of current I have is this intersection, the current that I am literally enclosing within my Amperian loop. So what I need to do is I need to actually find the current that I'm enclosing here. And it turns out we can do this as a ratio. The current we're enclosing is a ratio between the areas of our Amperian loop and our full loop. So let's call our full loop here, let's call this capital R. Okay, this is a common thing in physics, to have like a larger loop be a larger letter, capital letter. And if I keep that as big R, and I look at my ratios, I'm going to see that the ratio of my orange Amperian loop, that cross-sectional area is pi r squared. That's a little r. And if I take that as a ratio compared to the big loop, that's going to be pi r squared. This is my ratio of areas. So this gives me a fractional amount, like 0.5 or 0.4 or 0.7. And if I multiply that by the total current I had, or the current initially in the system, how much current is going through that wire, that's going to give me what I have enclosed in the circuit itself. And what's nice about this is we see some pi's go away on our end, which is wonderful. And if we do this with our equation, we're going to see that we're going to have B equals mu naught times the current enclosed over 2 pi r, just like before. But now, because I know what my current enclosed is, we can say that this B field inside the wire at some point is going to be equal to mu naught times the current enclosed, which is the total current, I, multiplied by the quantity r squared over r squared, and then this will be all over 2 pi little r. whenever we, mess around with this and simplify, what we're going to find is that an r and an r, the little r, is going to go away. And our final answer here is going to be mu naught I, and you're seeing what I'll do in a second, divided by 2 pi big R squared. These are all constants, so I'm putting them all together. And the thing that is actually different, or the thing that can change, is this is multiplied by little r, because I still have a little r left here. Okay? So this is actually my final equation. This will equal the B field at some inner radial distance. Okay? So if we're inside a wire, this is what we are going to have here. It's kind of interesting because if we were to plot this, if we were to plot a B field as a function of position, your B field is going to be linear when you're inside the wire. When you're inside the wire, this B field just grows linear, linear, linear. Once you hit the edge of your wire, well, now we know that's mu naught I over 2 pi r. It's going to fall off as a 1 over r value. So here it's a linear, it's proportional to r, and over on this side it's 1 over r. So kind of a neat way to look at that. Okay? But that's how we can use Ampere's law to give us a little bit more information about what's going on in our systems with these B fields. And it's just kind of a really simple, straightforward equation that we can make light of just because we know what the perimeter of a circle is. Woo! So with that, this here is finished. You can all take that. Adios, and take it easy.